Yeah, we'll get started on just talking about I guess some of the things in scikit-learn. Okay, and so you know I mentioned this earlier, but basically, you can just search the Google for sklearn. Okay, and the package here is scikit-learn. It's a very powerful machine learning package with all sorts of stuff in there. And so I just wanted to talk, just today, we'll talk a tiny bit about some of the features in model selection, primarily the idea of cross-validation, okay? And then we'll look at a couple simple classification algorithms to do some stuff there, okay? And so I'm going to start by importing NumPy and pandas, and then from sklearn, if you just do like import sklearn, there's like too much stuff, okay? So I'm going to pull the iris data set from sklearn. That's the kind of the classic Fisher's iris data, 150 observations of different irises, and then from model selection we'll pull train test split and cross-val score, and then we'll also take a look at the k-neighbors classifier, so that's KNN, and then the Gaussian naive Bayes classifiers as well. So this is, we'll start by, go ahead and just clearing everything. Restart and clear. And you can, and this is not to say like this is how you have to do anything, but I just want to kind of highlight some of these ideas. All right, and so so an important idea in machine learning is this idea of cross-validation. And the idea is you split your data into kind of a training set and a testing set, and you evaluate the performance of your model based on the test data or the validation data, okay? A lot of times, the diagram might look something, okay, is that, you've got, let's say this is your original data, okay, this is all data. A lot of times you'll kind of partition part of it off, and this will be train, and this will be test, okay, and usually kind of after you've split them up, because unlike your traditional statistics models, we're not going to be using p-values and likelihood ratio tests and things like that to kind of measure how good our model is. The performance of our models determined by how well is the model able to predict the values in the test data. Okay, so this is assuming some kind of supervised learning thing. All right, so we use the training data to fit our model, and then we use the model to predict the test. Okay, and so that's what we do, and oftentimes we will further split the training data into validation. We'll break this further up, okay, and this we might break into like different parts, and it will be something like this, okay. This will be the validation set, and this will be training, and this will be this part will be train, and this part will be train, and this part will be validation, so on and so forth with each piece, okay? So each of the 4 pieces gets to become a validation set. And this is kind of the idea behind cross-validation, okay? So you have like, this is 4-fold cross-validation. Okay, is this the first time anyone's heard of cross-validation? Okay, you guys have all been exposed to cross-validation in some form in some other class, right? Either 102B or 101C, I'm hoping. Kind of the idea of, I don't know, where else do you see cross-validation? I think. Okay, well anyway, it can be done very quickly for us in Python using sklearn's kind of these train test split tools, okay? And so here's just kind of an example of how it might work, okay? So I'm going to create a few arrays just to kind of give us a feel of how this works, okay? So imagine we've got some kind of X matrix, okay? And it's 6 rows, 2 columns, and we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then I've got a vector, or a one-dimensional array, y, which has the values 0 through 6. And I've also got another one-dimensional array z with the values of 0s and 1s. So this kind of is like classification labels. Z is kind of like classification labels, and then y can be thought of as, you know, maybe a regression problem where you're trying to predict these kinds of values, okay? Now obviously this is not a real data set. It's you know, too simple. But you can use this function, train test split, again, which we have imported from sklearn model selection, okay? You can use train test split and you put in one of the arrays. And so here, I'm going to put in this array, which has 6 rows and 2 columns. And I'm going to say the test size, I want 1/3 of my values to be in the test case, okay? And you can specify random state so that it's reproducible. This is kind of the equivalent of specifying a seed when you do some kind of randomization here, all right? And you'll notice that train test split returns a tuple, which we can unpack, okay? So we give it x, and it's going to return 2 parts. One is going to be the training data, and then the other part's going to be the test data, okay? And so when I run that there, we can see for the training data, it randomly selected, you know, 4, 0, 3, and 5, okay? So, you know, 4, 0, 3, and 5, those 4 rows ended up in the training data, and then the test data ends up being these 2 rows, okay? Rows 1 and 2. And then because I've specified the random state, we're going to get the same results. If I specified a different random state, we get different values, okay? Rows 1 and 4 end up in the test set, and the other rows end up in the training set, okay? So this is all randomized, okay? And so this is what we have. If I run the same thing on train test split on y, using the same random state and the same test size, it's going to split y accordingly as well, okay? And it ends up picking kind of the first elements 1 and 2 end up in the test case, and then as far as the training cases, we have elements 4, 0, 3, and 5. And we can see, indeed, that matches up with exactly how x was split, okay? So with train test split, we split x into, you know, 4 rows in the training and 2 rows in the test. And then with y, we also get 4 values in the training and 2 in the test, and they correspond to each other exactly. All right, we see that? Okay, so you can do it like this, all right? You can also just apply train test split at the same time. You can give train test split an X and a Y. You can give it kind of multiple arrays. Just tell it test size is this, random state 1, and you'll notice that the function will return a tuple, which you can unpack into 4 parts: X train, X test, Y train, and Y test. Okay, and so the result here will be exactly basically what we have up here. Okay, so you don't have to call it the same function twice. You can call it once and put in X and Y at the same time. Okay, and again, to kind of make sure that it's reproducible, I recommend the use of random state. Okay, and so this allows us to kind of split our data into training and test cases, and then you can fit the model to the training, and then you can see how well your model performs in predicting the test cases, okay, which is very important in terms of being able to see whether the model you have is good or bad, and is it, overfitting, is it, doing a poor job of making predictions. Okay. Over here I have when we created kind of our arrays, I created X and Y. You can also provide something like argument Z, okay, like a classification one, and use that in stratification. So here I've got X train, X test, Z train, and Z test. And here I'm going to split X and Z. Test size is 1/3 and random state is equal to 1. But notice I throw in this option stratify on Z, okay? And what this will make sure is that the different classifications or classes in Z are kind of equally represented, or as much as possible, right? And so in Z, half are zeros and half are ones, and it's going to try to preserve that kind of relationship when we split it, okay? And so this time, rather than putting rows 1 and 2 into the test case, okay, it recognizes that rows 1 and 2 are both of class 0. And so instead it puts in rows 1 and 3, okay, into the test case. And rows 1 and 3 will be 0 and 1, and then our training cases have, are 0, 1, 0, 1. So meaning, we have half of the values in our training are zeros and half the values are ones, and in our test cases also half are zeros and half are ones. And this might be some kind of property that's desirable when you do your train test split, right? So in your original data, it might be like you're looking to kind of predict if something is a failure, but maybe only 5% of the values in your data set are failures, right? And so when you do the random training and test split, just by random chance, you might get too many or too few failures, and that could affect the way it performs in predictions on the test case. And so you might be able to stratify on failures and make sure that 5% of the training cases are failures, and also in the test, 5% of test cases are failures as well. So that's a useful feature that we have, function train test split, okay? So here, I'm going to go ahead and I'm going to load up the iris data, the classic iris data set. And I think you guys are all familiar with the iris data. Has anyone not heard of the iris data at this point in your stats career? So we've all seen like the Fisher's iris, and we love it because it's like such a clean data set, right? There's 4 numeric predictor variables and 3 classes, and it's like the perfect example to do some kind of classification algorithm, right? If you do, maybe you guys are encountering this in your projects already, but real data is not as clean as things like the iris data. Things are a lot messier. You might have to do a bunch of cleanup and stuff. And by the way, regarding your projects and stuff, if you have questions about what your group should do, and or if you started something but you're not quite sure, feel free to come by my office. I know office hours are scheduled at certain times. I'm generally going to be in my office, between 11 and 3 p.m. on Mondays, Wednesdays, and Fridays. You can stop by, and if I'm busy, I'll let you know I'm busy. But if I'm able to help, I can help. Okay. And so, I'd much rather groups come and visit with questions and feedback, and if I see them doing something wrong, I can kind of steer that to be less wrong or do something right, rather than on the day of the presentation, I feel like something was not good. Okay, so. The iris data is stored as what's called a bunch, okay? A bunch is basically a dictionary, except associated with each key is like something that's not necessarily a single value or something, okay? It's like a dictionary, except you've got these keys and they're complex things like the data, okay? So, here's like the first 4 rows of the data, and we can just see it's a matrix with 4 columns, okay? And then the feature names are stored here, and you can do what are the feature names, and then we see that, okay, these 4 columns, the first one is sepal length, then we got sepal width, petal length, and petal width, and this is going to be useful in terms of classifying our observations. Okay, the target is an array where we've got the classifications 0, 1, and 2. Those are basically the 3 species, and they actually they come with names, right? And so you have Setosa, versicolor, and virginica as these things, and so these are all just parts of what's stored in the not the dictionary, the bunch. Okay. And then there's DSCR, which is a big kind of just a text file that lists off everything, and gives us, kind of the history and all of the stuff. The Fisher iris data set, which I guess came originally from 1936, the use of multiple measurements in taxonomic problems. Okay. So anyway, that's useful for us. Okay, so what I'm going to go ahead is I'm going to use train test split. We're going to split the X, the data. We're going to split the Y, the target. Okay. Test size, I'm going to say 20% of cases are going to be on, will be going into the test. So we have a total of 150 observations. So 30 observations I'll put in the test case. Okay, I just say random state is 1 arbitrary number, stratify, and we're going to stratify based on the target, so that each of the species, Setosa, versicolor, virginica, are kind of equally, or appropriately, proportionally represented. Okay, and so in the original data, they're equally represented: 50 Setosa, 50 versicolor, 50 virginica. And so when I do this kind of split, okay. Well, just quick quiz. What will be the dimensions of X train? Okay, so if I do X train shape, it will tell me what? How many rows? So I've got 20% in the test, which means 80% of 150, so 120, and then we got four predictors, right? So this should be 120 by 4, indeed. Okay, and then and then we can do kind of a bin count on Y test, and indeed it says we've got 10 in each of each case, right? So this is just NumPy's kind of like count how many unique things we've got, right? All right, so maybe we want to fit like a KNN classifier, and just for fun, we'll make a couple plots. Okay, so I'll import Seaborn and stuff. I'll take the X train and make a data frame out of it, and then we'll take the and then we'll label the columns using the feature names. Okay, and then and I can create a pair plot accordingly. And so this is just the training data. So there's only 120 things represented, and so we could see sepal length and sepal width and things like that. Okay, so to create the KNN classifier, we've imported kneighbors classifier a long time ago here, sklearn.neighbors kneighbors classifier, right? And so you don't have to use that, but so under classification, there's all sorts of classification things that we can use, right? These are all supervised learning methods. And so we've got all of these things under nearest neighbors. And so nearest neighbors classifying, we've got all sorts of options here. Okay, but anyway, so there's any of these things. We're just going to use the KNN thing. Okay, nearest neighbors classifier. The kneighbors classifier. I guess there's radius neighbors classifier. I'm not. Okay. So so kneighbors classifier, you say like I want the 5 nearest neighbors, and then the radius neighbors classifier says here's a radius, and however many points fall within this radius, use that to kind of vote, if that makes sense, right? So if you're in a densely packed neighborhood, using like the 5 nearest neighbors, you might only have a small circle, or if you use a constant radius in the dense neighborhood, you'll have like a bunch of neighbors. Okay, but then if you go out to a sparse neighborhood, if you keep k equal to 5, you might have to draw a big radius, whereas using a constant radius, you might only have 1 neighbor within that radius or something. Okay, so these are just different options. It doesn't matter, but there you go. Kneighbors classifier. We'll go ahead and use that. And so to run it, all we do is we initialize and we say I want the kneighbors classifier, and you can see there's all sorts of options, but we're just going to specify neighbors equals 5, right? So here under kneighbors, by default we've got neighbors equals 5. You can change things such as the weight and leaf size. I don't actually know what some of these things are, but in the regular kneighbors classifier, if you've got the 5 nearest neighbors, you take all 5 votes and you just look at how many which classification got the most votes. But you can modify that so that the neighbors that are closer, the near neighbors, get heavier weighted votes and things like that. So these are just different options. We'll just stick with the vanilla kneighbors classifier with 5 nearest neighbors. Okay, and if you do this, it doesn't actually do anything. Okay, you print it out and it just says, all right, this is what your kneighbors classifier is running off of. Okay, these are all the arguments. You only specify neighbors equals 5, which is actually the default anyway. And so these are all the arguments that it's running with. Okay, and then what we do is we run knn.fit. So this is the classifier that we've initialized, and we have to call fit, and that will then take the time to try to figure out how to kind of the values that it's going to predict here. So we're going to do xtrain. All right, and so it's done there, and now we ask to make predictions. Okay, and so we're going to say predict on X test. Okay, so this is kind of the test cases. And so KNN is a slow algorithm when it comes to making predictions, because each prediction requires you to measure the distance to everything in the training data, but that's okay. You know, we only have 120 values in our training data, so it's probably pretty easy. Okay, so it does it, and these are the predictions that it's made, and we can see, you know, what were the original values, right? And we can do a comparison value by I, and we can say, okay, it predicted 2 and its actual value was 2, it predicted 0, its actual value was 0, and things like that. And then we can say, okay, did it make any misclassifications? And we can see this value, it predicted 1, but in actuality it was a 2. Okay, so I don't know if there's other things. There's in sklearn for classification tests, you know, a useful thing for the metric is the confusion matrix, right? You compare what did it predict versus what did it, what was the actual value, okay? And so for here, I'm going to import confusion matrix from sklearn metrics, all right? And again, just like everything else, I refer you to the documentation. All right, so we've got for this, and then so the confusion matrix, you just provide it the actual values and the predicted values. You just kind of throw those in there, and then it lines them up. And basically what you're hoping for is values along the diagonal. So this means when it was class 0, it actually was class 0 10 times. And when it was class 1, it was predicted as class 1 10 times. And here we can see when it was class 2, so this is, the row is kind of, when the answer is class 2, it predicted class 1 once, okay? And it predicted 2 9 times. And so, and that refers to this, right? So the actual value was class 2, and it predicted 1 time. And so this, we've got 1 out of 30, we've made 1 mistake. Okay. So that's what we have there, right? We could try doing the whole thing again, this time using only one nearest neighbor. And so we'll have KNN with number of neighbors equal to 1, we'll fit it, and then we'll produce the confusion matrix, right? And we get the same kind of thing. We have one misclassification out of 30. This time I can say I want to use the 25 nearest neighbors. All right, probably not the best idea, but we can go ahead and do the same kind of thing. And when we do this, it makes 2 mistakes. Okay. Is that okay with what's happening? So this is just kind of a quick way to kind of assess your k-nearest neighbor's prediction performance. Okay, and this highly depends on how our data is split between training and test, right? It's just kind of random, and so, you know, we might get different performance based on a different train test split. Okay, you know, a common issue with the KNN classifier is, you know, what value of k should we use, right? Someone says maybe we should try k with 1 neighbor or 2 neighbors or 3 neighbors, so on and so forth. And so you could go through this process manually and say, okay, this was the performance I had when k was 1. This is the performance I had when k was 2. This is the performance I had when k was 3, and test these out yourself. But that already, just talking about it, makes me feel like this is going to be a tedious task, okay? And so sklearn comes with something called grid search cross-validation, grid search CV. And what this does is it will automatically kind of search for parameter values. So you tell it, I want you to try out KNN where k is 1, and KNN where k is 2 and 3 and 4, and you give it all of the values that you want it to test, okay? And some of these models will have multiple values. So you can say, I want you to try it for k equal to 1, 2, 3, 4, 5. I want you to try the uniform weights versus the distance-based weights. I want you to try all of these different models. Some of these other models you can specify a gamma value and a c value and a lambda value. You can say, I want you to try all of these different values. Okay, and so this is going to be called a grid search because if you have multiple parameters, like if you've got the k parameter and let's say you've got a lambda parameter, you can say, I want you to try out 10 k parameters and I want you to try out 4 lambda parameters, and it's going to do all kind of 10 times 4, 40 combinations of the k and the lambda values. Okay, and then if there's another parameter, like you wanted to have like 3 gamma values, right? So you've got k being 1 through 10, lambda being 1, 2, 3, or 4, and then gamma being 10, 100, or 1,000. It's going to do all possible combinations. So that will be 10 times 4 times 3, and it will do 120 combinations automatically for you. And all of these things, you give it a way to measure performance. You give it a metric, and it's going to test every single model. And so this could take a very long time if you've got a lot of parameters and values to search, but it'll test every single model. It will keep track of the metric, its performance with all of those different values, and then it will return back and tell you which one was the best. Okay, so so here I just got one parameter. We're going to just try different values of k. We're going to try k going from 1 to 50. Okay, and so so I'm going to use this function called grid search. My battery just died. I'll use the function called grid search. And so I give it this, I give it a dictionary that's going to be, what's this also? These batteries are also down. All my batteries are dead. Okay. So here I give it a dictionary of kind of the values I wanted to try. So I just say neighbors is going to be the values 1 through 50. I initialize the k-neighbors classifier, and I don't specify the number of neighbors in here. Okay. And here, instead of writing n neighbors, so back here I said, n neighbors is equal to 25. What it's going to do is it's going to take this exact name and plug it in as one of the arguments here. Okay, so we initialize a k-neighbors classifier, and then I call grid search CV, and we're going to say k and n, and it's going to and parameter grid, and it's going to try out every value inside here. N neighbors is going to go anywhere from 1 through 50, and it's going to do 5-fold cross-validation. All right, does that kind of make sense? What this is doing here, can and CV. So it's gonna run that. Okay, so it actually hasn't done anything yet. We have to call it on our training and test data. Okay, so here or just our training. So we've got 120 values in our training data, and it's going to do 5-fold cross-validation. So we go ahead and we do that. It takes a little bit of time, but now it's done. Okay, and we ask which one performed the best, and it tells me it performed the best when n number of neighbors is 13. Okay, and what was the best score? Okay, and as far as the k and n goes, this is like the same as everything else. It looks like it got 98% accuracy. Okay, and so with 13 nearest neighbors, for the entire training data, I guess it made 118 out of 120 predictions correctly. Okay, so that's what we're getting here. Okay, and when we run it on the test data, we also get we still get one mistake here. But let's see. You can ask for the cross-validation scores, and the way the cross-validation scores work is with fivefold cross-validation. It splits the the 120 values. You divide that by 5, and so you got 24. And basically, it means it predicted 23 out of 24 correctly here, 24 out of 24, 24 out of 24, 100%, 100%, and it made one mistake. So overall, the average of these numbers, ends up being the same as 118 over 120. Okay. So you can try out kind of these different parameter values. If you wanted to, you could specify. So here it was number of neighbors 13. Under nearest neighbors, I can change it. We can do weights, and we can try uniform versus distance. Okay, and so I could complicate my parameter grid with weights is uniform or distance. Okay, and I think so that runs, and now it will tell me okay, I guess the best was 13 neighbors where weights was uniform. So we're going to get the same kind of, I guess that's what we get for this particular training data. Okay, but you can, so it tests across all possible values here. Okay. I guess just quickly, I can do kind of the Gaussian naive Bayes classifier, right? And so, if we wanted to check the naive Bayes classifier, so we'll just do the Gaussian naive Bayes classifier, and we can look at the kind of the help command here, and these are the different attributes that Gaussian naive Bayes use, and so here I just kind of initialize an empty Gaussian naive Bayes model, and then you always basically everything in sklearn goes with you initialize it with arguments, and here I'm just going to use the defaults, and then you fit it to your training data, and then you call predict on the prediction on your test data. Okay, and when I do the confusion matrix, we also have one mistake. We can ask, what is its cross-validation performance? Okay, and it's not super great. It gets 95% classification performance, which is, I guess, not bad. Can't complain about that. But we've seen ones that were better. And so as far as and with the Gaussian naive Bayes, it's basically using the the standard deviation estimate and the mean estimate from the training data to come up with its predictions. But these are different options, and all of these things, depending on the kind of data that you have. Like if you had categorical data, you could do the multinomial naive Bayes and things like that. Okay, and this isn't like a real machine learning course, so I'm not going to be like covering all of these different methods, but I'm hoping you've at least heard of some of these things, right? Like the KNN and the Gaussian naive Bayes, and some of these things. And now we have a framework to kind of implement and at least use these models within Python and sklearn. Okay, and so these things exist, and they're there. You don't have to code any of these algorithms by hand. These are all very high quality, high performing modules and functions, and there's very good documentation available. And so my encouragement is, even if it's something we haven't covered or you haven't learned, probably somewhere out there on the internet has created a tutorial on at least getting started, and you can probably adapt it and modify it to your needs. The biggest hurdle in a lot of these things is getting your data to conform into the format that sklearn likes. That you need kind of a matrix of your x variables, and then a separate matrix or separate vector of the y target values that you need to plug into kind of the model.fit and the model.predict. So that's that. I guess I'll continue on a little bit more on sklearn's stuff for the rest of the week. If you guys have special requests or suggestions for topics to cover, let me know. We're limited in what we can do, and then probably next week I'll cover SQL a little bit. We probably only need like 1 or 2 lectures total on it, to be honest. It's I think pretty easy to pick up and cover. So and again, don't hesitate to visit me if you've got questions about your project and things like that. I think everybody's scheduled their final project presentation, and so the final project, the report, is due whenever your group has its presentation scheduled. Okay, we'll see you in a bit.